Welcome, everyone. I'd like to introduce our speaker today, Gita Mallya, who is approaching the completion of her master's research and thesis here in the department. Gita came to Viticulture and Enology like many of our students do, coming from a slightly different background. Gita graduated from UC Davis with a degree in plant biology, and while she was undergoing those studies, she became more and more familiar with viticulture and enology, and eventually completed some internships either during her undergraduate work at Revolution Wines and then just after graduation at Schramsberg Cellars. While she has been in the department, she's also been an important contributor and leader to our student organization, Devo. She's been the vineyard manager, the VEN290 seminar series coordinator, and more recently, she has been one of the founders of the Women in Wine at UC Davis and is currently the financial officer. So Gita will be giving a talk today about the use and understanding of redox potential in winemaking. And just want to point out, like many of our students over the past year, her leadership skills have come to good use in that she's been able to conduct all of this work with very little kind of in-person instruction from either me or Ben over the past 16 months. I think Gita and I met maybe 2 or 3 times maximum in the lab to kind of help her become familiar with some of the equipment and lab setup, and she has taken it from there. And so, Gita, I will let you continue and take the presentation. Thank you so much.
Thanks for that lovely introduction. Hi, everyone. Thanks for being here today. My name is Gita Mallya, and I've been working in the Montpetit and Renaudin lab groups. Today, I'll be speaking about the use of redox potential to predict fermentation outcomes in relation to the initial juice conditions. So first, here's an overview of what I'll be talking about, a little introduction on what redox is and why it's important. And then we'll get into the design of my experiment, the results and discussion, and then future work. So I use this term, but what exactly is redox? In general chemistry, we learned that redox stands for reduction oxidation, where reduction causes a gain in electrons and oxidation is loss of electrons. So the terms redox and ORP, or oxidation reduction potential, are often used interchangeably, and you'll see it measured as EH, or millivolts, in the literature. So ORP is the quantifiable measurement of the tendency of a molecule or ion to gain or lose electrons. And so we see that in this reaction, this compound here is losing them to this compound, and which gains them. And this is based on an inherent affinity for these electrons. So why should we care about the electron status of the different compounds in wine? Well, just as microbes have optimal ranges for pH, temperature, sugar, alcohol content, etc., it's also been shown that microbes have optimal redox levels as well. So this diagram shows the balance between pH and redox potential that the microbes can grow in. And as you all likely know, pH is an important factor to consider with how well a given microbe will be able to survive in an environment. So in many industries, a lot of time is spent ensuring that the pH is at an optimal level for their bioprocess. And it's been found that there's also a range for redox, which is a variable that's not as widely considered. Because of this existence of an optimal range, it makes sense that we would try to measure it and understand it just as we do for pH. And then there's also this fact that microbes react to and affect the environment they're in by the different compounds that they produce during metabolism. So during fermentation, one of the biggest contributors to the redox level of the solution is the NAD+ NADH couple. This coenzyme is an extremely important part of metabolism as an electron carrier. And since yeast make up such a large portion of the solution during fermentation and are vigorously metabolizing the sugars into alcohol, the status of the compound is one of the biggest determinants of the redox level. So the proton gradient that the yeast create to generate ATP, as well as the compounds that are created as a result of metabolism, affect the solution. So the intracellular redox potential of the yeast will be different than that of the solution. The yeast will create a reductive environment by depleting the oxygen and pumping out reducing compounds like glutathione. And you can think of this as another way to narrow the niche of what organisms can grow in the solution, much like when alcohol is produced in fermentation in order to limit other microbes' growth. And so a low redox potential could lead to H2S production, either through yeast metabolism or chemical formation, which is a common concern for winemakers. So this graph shows the fraction in the oxidized form of some of the important compounds in the different stages of winemaking. During fermentation, we see that the ORP levels vary between -200 and +200 here. And then the levels are a little bit more positive for finished wine from about 200 to 400. We see in this green square the intracellular environment for the yeast. And we see that it's much lower in ORP than the juice or wine environment, which is a factor in why redox gets driven downwards in fermentation, since they're putting out compounds into the environment. And the NADH reaction, as well as other reactions related to metabolism, need a certain redox environment to proceed. So if this is the basis of the yeast metabolism, it makes sense that the intracellular environment would be different than the extracellular environment. So in this purple square that shows fermentation, we see that the main formin fraction is copper plus down here. And in the wine condition, this is aging storage, we see that the main form will be copper 2 plus up here. And so the form is pretty strongly in one form or the other, which could be of interest if we're thinking about different metal reactions that could be occurring during fermentation or during aging. The change from juice to wine in fermentation is pretty drastic from a redox and just composition perspective. Whereas in the finished wine, yes, there are important reactions occurring, but the change in redox is less extreme and could be happening over many years. And this is why it's important to consider the initial environment in regards to how it affects the final product and what compounds you start with when you start the aging process. So it's also easier to study 1 to 2 week fermentations rather than years of aging in the context of a master's thesis. So we focused in on fermentation. But like I said earlier, here we see this variable, redox potential, that's changing drastically during the course of fermentation. And it's not being monitored or controlled. We monitor and adjust pH, we monitor and adjust temperature. And here we have another opportunity for better control over the fermentation by using redox. So currently in the industry, the two main process parameters that are used by winemakers to monitor fermentations are temperature and Brix. A process parameter can be defined as a metric used to track the progression and make informed decisions about a bioprocess. In the wine industry, these metrics are important for understanding the fermentation's health and progression. And with the current parameters, we can see changes in the fermentation and predict problems. But often when we see these changes in Brix, there's a significant delay in when the problem actually begins, and then when it's obvious enough for us to see it and then try to correct it. So our hope is that redox data will increase this response time as an additional process parameter to use. Redox as a parameter considers pH, dissolved oxygen, temperature, and chemical half reactions. So we've been talking at a pretty narrowed level, so we'll bring it back to a more broad view. Why should winemakers and viticulturalists care about ORP? In a few words, the compounds that are on and in the grapes when grown, as well as the environment, practices, additives the winery used, will influence the ORP of the wine. So we know that yeast will try to modify their environment to dominate the niche, and depending on the wine environment, this will affect redox in different ways. This slide shows the cyclical relationship where ORP influences microbial growth, and microbial growth influences the environment from the compounds they're producing, from metabolism and in response to the solution. So the initial conditions are important to consider in how the fermentation might proceed. So if the initial nutrient ratios, metal ratios, pH, etc., set the stage for a low redox, the yeast might respond by driving the redox low, which could then cause H2S production, other reductive qualities, stress protection in the yeast, since the environment is now more difficult to ferment in. So the things I've mentioned are things that we know about redox. So what are the remaining questions? In winemaking, we don't know if or how yeast strain affects the ORP, whether grape variety influences it, if certain nutrient concentrations or ratios influence it, how metals and their ratios affect it, how pH affects the redox curves and progression. What do redox curves look like for spontaneous versus non-spontaneous fermentations? And what do the ORP curves look like under different situations where a juice is a challenging environment? And do they differ between the types of challenges? And all of these things can be taken all the way back to the grape composition. So if the compounds that are present from the grapes are such a contributing factor to redox and the health of the fermentation, it might be important for viticulturalists even to understand how berry composition and vineyard sprays or additives affect redox and then grape quality in order to assure better wine quality, which is what the winemakers will be concerned with. And so we can think about this in terms of site too, site influencing the finished wine. The different microbial interactions, metals, vineyard practices, winery practices will all ultimately impact the redox potential of the juice and therefore the wine. So do different sites have this potential for redox to be driven lower than normal, which leads to reductive qualities? Or do some sites have more of an ability to buffer these reactions? And maybe the problems that occur can be addressed through compensation and other practices like strain. And right now we don't know the answer to these questions, but it naturally led us to the creation of this project and trying to answer whether redox data can be used to monitor and predict the outcome of fermentations. Especially if it's prior to Brix indication, this could be a very powerful tool for the industry since millions of dollars every year are lost to these issues, and prediction could be a great tool. So these are the goals that were created at the beginning of the project, which were to create both success and failure fermentation situations, and then observe the resulting redox curves to try to understand differences and whether it might be able to be used as a prediction tool. So these experiments were carried out in 1 liter bioreactors, shown in this picture right here. And these vessels gave me a lot of control over the fermentation since they were small and also autoclavable, which meant that they could be sterilized. In this picture, this vessel itself is glass. There are these tubes running between each that are connected to a water bath to control the temperature. And then we have this silver piece here on top, which is a motor that spins down here to ensure a well-mixed fermentation. And then these red cables in the back actually connect to the bioreactors. There's probes behind this motor. And those probes are measuring the ORP of the solution. And they measure continuously, so all of the data that will be shown are taken at 1-minute intervals throughout the entire fermentation. And Brix were taken every day at the 24-hour mark and twice a day at the 12-hour mark for the nitrogen trials, which I'll talk about later. So in order to have control over the contents of the fermentation, the medium, the additions, pH, age of the media, etc., we used minimal must media or synthetic media. And this is a lab-made solution That's considered a grape juice-like medium, which is very defined, and this aided in really focusing on variations in microbiology rather than variations in the juice composition. So triple M, this synthetic must, has been used in other experiments previously, and there's a standard recipe to make this so that it ensures there's uniformity in the media. It starts at a Brix level of about 21 to 22, and all of these experiments were performed at a temperature of about 21 degrees Celsius. So here's a little bit more information about the probes. You can see it back here, inserted into the bioreactor. This is what it looks like when it's out of the bioreactor. Here's again the tube that was used for cooling. And then these pieces unscrew so that you can take samples or Brix measurements in my case. So as for the electronics, the Redox probes use a silver chloride reference solution with a platinum band. There are other probes available that use a gold band or a hydrogen reference standard. However, the ones that we use have more suitable qualities for the experiments that were run. And they are commercially available for purchase. And then the silver chloride reference has a range of -500 to +900 seen on this range. And that's well within the juice and wine range, which is generally from -200 to +400 at most. The probe itself is designed to not impact the redox of the solution from being inserted, since it's made out of glass and has a platinum band at the end, which won't be notably oxidized or reduced. So you may have heard of dissolved oxygen probes and their use in the industry. And this is a good thing to keep track of, as this is one of the factors that contribute to redox measurements. But the redox probes are a better measure of they're a better measurement, since dissolved oxygen will hit a 0 point, where redox can go negative and give a better indication of what's happening past that point where dissolved oxygen is no longer there. So here's a graph that shows the general idea of the data that the probes give. This graph is from a study by Liu et al. And the curve is fairly typical. We see that redox starts at positively at this high, where with this red line, and drops to a low of about -150 millivolts when the biomass reaches its highest point, shown by this green line. And then as the fermentation finishes, we see this rise in redox again. So this is, again, very typical. So speaking of biomass, in terms of the yeast strains used, they were all chosen based on their use in industry and research, or for known characteristics that they present. So included were hybrids, ones used for Pinot Noir, Chardonnay, and others to ensure that there was a diversity in the strains used. The ones that were selected were EC11118, RC212, CY3079, Elixir, and Montrachet. So we have representation from Bionis, some pure Saccharomyces cerevisiae strains, both that are generally used in reds and whites. We have this hybrid strain from the university, and then Montrachet is also a pure strain of Saccharomyces cerevisiae, and it's been in the culture collection for decades now. So we have this initial question of, what do failure and success fermentations look like in regard to ORP? So the first data set that I wanted to show was a trial using RC212 yeast. This yeast is most commonly used in Pinot Noir fermentations and is said to have a medium nutrient demand and an alcohol tolerance of around 16%. On the Scott Lab website, it mentions that, quote, timely nutrient additions are recommended to avoid potential H2S production. And across the trials that I ran, RC212 was pretty hit or miss in terms of whether the fermentation was healthy or sluggish or stuck. So it was interesting to compare the different curves. Many of the earlier runs, including this one, were at a pH of 3.25, which, as the winemakers in the audience know, it's definitely on the low end and a challenging environment for the yeast to ferment in. So this led to some of the fermentations completing and others sticking for undetermined reasons. But this was beneficial as we have to know what failure redox curves look like in order to be able to predict them in the future. So more runs were completed at pH values of 3.5 and 3.75 to observe the differences, and we'll talk more about that later. So in this graph, the solid yellow curve represents the ORP, and then this dotted line indicates the Brix level. Again, it's a good representation of what a successful fermentation looks like. It has that high start at around positive 300. Around day 3, we hit this redox low of about negative 150 millivolts. And then when the fermentation hits about 5 Brix, we see that the redox starts to rise again. So this next overlay shows a replicate of the first. As we can see, the data looks nearly the same. And it shows that the initial data was repeatable. Both of these replicates were successful and went to completion. So again, the same drop, hits a low, and then starts to rise again. And then this next overlay shows a run that did not go to completion. So if you focus in on the first 24 hours from 8:15 to 8:16 about, we see that the Brix data doesn't change very much, but there is great variability in the redox data between runs, the ones that completed and the one that didn't. So we can also see that the redox level begins to rise at almost 12 Brix, which is much sooner than those that complete. So in this one that stuck, we see this late drop in redox and then an early rise. And that could indicate problems. So from the Brix data, we may have predicted on day 3 or 4 that the fermentation would struggle, but had we used redox data to monitor, we would have known at least 24 hours sooner, and that could mean taking remedial approaches sooner, which would increase the overall effectiveness of the treatment and potentially save a lot of time and money. So one thing I wanted to point out was these kind of undulations in the data, these waves, as it proceeds. And we see these waves in the morning, which then drop off at night. And initially this was thought to be a product of how the sampling was occurring. So each time Brix data was taken, I would have to unscrew a piece of the lid, which would expose it to oxygen, and which we learned earlier, that would raise the redox level. So some literature points to this existence of a circadian rhythm in yeast metabolism. And this was an initial thought or explanation, but after seeing this in both my and my colleagues' experiments, we saw that the waves were greatly reduced by blocking the light from the bioreactors that was coming from these big, beautiful windows in the RMI building. So this led us to believe that there was a technical issue and a sunlight component that influenced these redox readings. So you'll see in the nitrogen data, which I'll show later, that the curve is much smoother, and earlier runs will have these kind of undulations. So one of the next variables we can consider is pH and how it influences the curves. The values used were 3.25, 3.5, and 3.75 to cover the range of pH values in the industry. So this next set of data is comparing the same strain across different pH values. This is the run with Elixir, and we see that as pH increases, the redox lines drop slightly lower. So the ones at 3.5 and 3.75 finish on day 7, and the one at 3.25 did eventually finish on day 11. So the two at the higher Brix were pretty comparable. They were both healthy, quick fermentations. And then we see this difference with the one at 3.25. The fermentation was sluggish, as we see in the beginning. There's this hesitation before it drops to its minimum, and its minimum is much higher than the other two. The low point it gets to is about -150 on day 4 or 5, while the other two are -200 by day 3. So again, if we were monitoring fermentation with redox curves, we would have seen on day 2 into 3 that there would be something wrong, since we see this plateau in redox. So the last graph I showed was using Elixir, and this graph shows the same parameters using RC212. So the two strains in the same conditions are interesting to compare, since Elixir was such a robust fermenter, while RC212 was one of the weaker ones that didn't always finish. So in this graph, we see a similar thing where the fermentation at 3.25 Brix started to drop late, as we see here, and have this plateau. And then once it got to its minimum, it was at a more positive value than the other two. Interestingly, the fermentation at 3.75 drops late as well, as we see here. But once it starts dropping, it has this continuous downward movement, whereas that's not the case in the 3.25. This could just be a difference in the strain, but it would be important to replicate this trial to explore this difference. It might be that this strain really only operates at an optimal level of 3.5, very small window, but again, more replicates would be important to see if this was common. We also see that towards the end of fermentation, the one at 3.25 is at a more positive level than the other two. While they're rising from this low point, this is still higher. And the 3.5 and 3.75 fermentations finished in about 7 days, and the one at 3.25 took 15 days to complete. So this slide is just the two pH graphs compared. We can see the plateau in the first few days of the ones that struggled in each run, so right here and here. And then there's also this rise in redox towards the end that are similar to the ones that complete, even if the sugar level is still high. So since these strains are fairly different, it's encouraging for prediction purposes in the future that they show very similar trends. So another question that could be posed was, what does nitrogen limitation look like in redox curves? So for this trial, levels of 13, 26, and 52 milligrams per liter were observed, whereas in other trials, the nitrogen content was at about 208 milligrams per liter. So as I was saying earlier, this is the first run where the light was blocked, which led to this much smoother line throughout the fermentation. We don't see those big waves going down the data. But this curve is interesting in other regards as well. So we can look at the beginning of the curve again and see that it's pretty standard compared to the ones that we've seen before, with this sharp drop off to a minimum by day 3. And the difference, though, is that the minimum that these curves get to is -100, which is much more positive than previous runs, which could be as low as -200. The strain used for this experiment was Elixir, since it's a robust fermenter similar to EC111A. And across the other experiments, it was shown that the general shape of the redox curve is pretty much the same across the different strains. And since the strain is a strong fermenter, it's likely that if this one struggled in a trial, the others would as well. So in normal nitrogen conditions, we see the redox level drop down to about -200, yet all of these nitrogen limited runs only get down to -100. And this is interesting, especially because They all reach this level, and it's not a stepwise increase based on the amount of nitrogen. We see the ones at 52 milligrams per liter finish slightly sooner than the others. However, these are still 11 to 12 day fermentations, with the other ones finishing on day 13. So there are slight differences in the beginning with the curves. However, it mostly shows that the 13 and 26 milligram per liter conditions were acting similarly. Right here, we see those differences, but we see that it's 26 and 13 that are acting very similar, and they all eventually are at this line of negative 100. And this data shows us that there's this range of minimum redox potential that the yeast will hit during fermentation, with the most positive being negative 100, meaning that something in the fermentation environment is ensuring the juice gets down to at least negative 100. We see that in a run with the same pH of 3.5 and a normal nitrogen content of 208 milligrams per liter, the fermentation proceeds faster, as well as the minimum redox level being much more negative at negative 200. So this one is at 100, which would be up here, and it goes all the way down to negative 200 at the normal nitrogen concentration. So the tables at the bottom show the cell density at 0 Brix for all of the trials. And these values were similar to the day 3 cell density values, which is when the bulk of the biomass is created. And the nitrogen limited trials had a slightly smaller population. However, the difference is very slight since they're all in the same order of magnitude, aside from the most nitrogen limited of 13 milligrams per liter. But this suggests that the nitrogen is important in driving redox lower, but it wasn't just a matter of the cell density in the solution. So the values of nitrogen in this trial were very low, as you can see, and we were actually expecting a failure outcome rather than just a sluggish fermentation. Aside from the nitrogen, it wasn't a very challenging environment. The pH was at 3.5. All of the other variables were conducive to a healthy fermentation. And this is where a juice and the synthetic media might differ. We might know that these concentrations are too little in juice, and this could lead to more projects in the future. But the synthetic media in this case is important in these early stages in order to manipulate one variable at a time and be able to make the same conditions week after week, which is not something you'd be able to do effectively with juice. So something interesting to note is the difference between the pH and nitrogen trials. Here we see that the yeast have no problem driving the redox lower. It's just that the minimum is higher than normal levels, whereas with the pH trials, we saw this hesitation in the initial drop where it might plateau, and then another like early rise in the redox. So what did we learn from all of this? The conclusions made were that redox data is a viable process parameter that has the potential to predict problem fermentations sooner than would slowing sugar consumption. And redox curves show similar repeatable trends that vary across strain and pH, which could allow for diagnostics in the future. This research is definitely still in its fledgling state, and there's a lot of research that could still be done to bolster the usefulness of redox as a process parameter. Things like refining the nitrogen study to observe failure and not just sluggishness, and see what that looks like on a curve. Seeing the tipping point of nitrogen concentration, where it's no longer at 200 and goes to negative 100 instead. And we could also look at different nutrient deficiencies and metal ratios to see if they have distinctive curves. The use of mixed fermentations or other strains could be another trial. And then this last point is using computer algorithms and machine learning to predict failure. And this point is actually one of the most intriguing to me personally, since it really automates the redox data and would require less scrutiny of the data by the operators. And so they wouldn't have to know quite as much about the different patterns in the curves. And we've actually been in contact with a lab in the computer science department who thinks that this work is achievable, which is very exciting. And then I just wanted to take a moment to acknowledge those who have been so instrumental in helping me with this project. Ben Monpetit and Ron Rennebaum, the two best mentors I could have asked for. They were always there to guide me in the right direction and answer my frantic Slack messages. Both of them have offered me great advice, and I'm grateful to have been a part of their lab and work closely with them. The others that were critical to this project, James Nelson, Kim Marinelli, Andre Knosen, Bob Coleman, Gordon Walker, Roger Bolton, thank you all for your expertise and time. And thank you to my fellow graduates who have made my time here unforgettable and rewarding. Thank you to my family for their continued support. And then finally, thank you to Wine Spectator, the American Society of Enology and Viticulture, and Jastrow Shields for their funding and support.
Great, thank you, Gita. Wonderful research and very nice presentation. We have time for questions and comments. You can either unmute yourself and ask them directly or place them in the chat.
Gita, I thought that last point you made on artificial intelligence being used in these systems is really interesting. When do you think it would be possible to start seeing those applications in wineries?
Yeah, as far as their use in the industry, I'm not sure, but it was definitely on the agenda to look into this year, and we were hoping to kind of start making these simulations within the context of this project. Unfortunately, there wasn't enough time to do that, but I can definitely see this lab continuing with the work and working with the computer science department, and I think it could be very soon that we see prediction models being made.
Can I ask a follow-up to that?
Yeah.
Do you think, like, you're set up with those tiny little fermenters,
Mm-hmm.
do you think large industrial wineries could potentially use that type of equipment to make small fermentations to sort of predict what's going to happen in their much larger tanks in advance?
Yeah, definitely. That's already being done in a few wineries. Bob Coleman actually works with Redox at the industry level, and he has a bioreactor. And so, yeah, mini fermentations are being used to predict the industrial scale.
All right, I'm gonna ask another one because I was curious about something. So, like you said, pH has an impact. So there's, obviously some sort of like terroir signature, but I'm wondering along those lines, like, would different varieties and different places have unique signatures?
Yeah, I definitely think that different varieties, because they have different compositions as well. So different varieties have different aromatic compounds as well as metal content. And so I think that all just contributes to this idea of site, which, as I mentioned a lot, that all of these things are influencing the final wine. And so I definitely think variety would affect this. And I think that might be the next step in these projects, after we kind of understand what's happening in the synthetic media a little bit more. Moving to juice and understanding difference in variety would be important.
Thank you. Great job.
Thanks.
Any more questions? Still have a few minutes. I guess, Gita, I know that you mentioned that you were excited about the modeling and prediction. Are there experimental aspects, I guess, of your list or others that you would be most excited about, and why?
Experimental aspects in terms of the computer aspect?
No,
or
just
generally?
the fermentation aspect, yeah, and the yeast aspect.
Yeah, the nitrogen data that we've been collecting was the newest run, and I think that the results from that trial raised a lot of questions. So I think varying nitrogen content and maybe even adjusting the strain would be really interesting, because we see that minimum redox that's not stepwise, and I just find that really interesting. So I think that would be an interesting trial. And then, yeah, I think there are a lot of different ways. I think metal ratios would also be of an interest because of the different additives and things that happen in the vineyard and how that might influence redox levels and prediction. So I think those are two good future directions.
Great, thanks. Does anyone in the audience have any questions? If not, we can congratulate Gita and thank you for the wonderful presentation.
Thank you.
Yeah, well done, Gita. Congratulations. Very impressive amount of work considering everything that was going on this year. Yeah, well done.
Thank you.
Good. I will finish here then. Okay, guys. Thank you
Okay.
very much, Gita. Yeah, see you around. Take care.
Thank
Bye-bye.
you.
Bye.
Bye-bye.
Congrats, Gita.
Thanks.